Now suppose that we're estimating this relationship, yi is equal to beta 0 plus beta 1 xi plus ui, but the true data generating process is this yi is equal to beta 0 plus beta 1 xi plus beta 2 zi plus ei. So in other words, we've not included this z term in our specification. Now the OLS estimator, if we're estimating this specification, is just given by beta 1 hat is equal to the sum of the yi's minus y bars times by the x minus x bars over the sum of the x minus x bar squared. Now a good place to start in any problem where we're trying to examine consistency is by substituting in the data generating process into our estimator. So what we're going to do is we're going to substitute our data generating process here in the place of y within our estimator. So we can rewrite this as being equal to the sum from I is equal to 1 to n, and then we're going to substitute in for yi and y bar. So we're going to find the sample mean of this, and we're going to subtract it from each individual observation of y. And what we'll get is beta 1 times by xi minus x bar plus beta 2 times by zi minus z bar plus ei minus e bar, all multiplied by xi minus x bar. And then that's all divided through by the sum of the x minus x bar squared. Now we've got a whole mess of terms on the numerator, so we're going to multiply out the numerator to try and simplify things. So we've got beta 1 times by xi minus x bar times by xi minus x bar. We've got beta 2 times by zi minus z bar times by xi minus x bar, and we've got ei minus e bar times by xi minus x bar. So we can rewrite this as being equal to beta 1 times by the sum of xi minus x bar times by xi minus x bar. So that's just beta 1 times by the sum of the xi minus x bar squared over the sum of the x minus x bar squared. So those are going to cancel, plus beta 2 times by the sum of zi minus z bar times by xi minus x bar. So that's beta 2 times by the sum from I is equal to 1 to n of zi minus z bar xi minus x bar over the sum of the x minus x bar squared, plus then we've got the sum of the ei minus e bar times by xi minus x bar. So we've got the sum of ei minus e bar xi minus x bar over the sum of the x minus x bar squared. And we said before that these two are the same, so they cancel. So this is going to be equal to beta 1 plus a whole load of stuff. So beta 1 plus beta 2 times by the sum from I is equal to 1 to n of zi minus z bar xi minus x bar over the sum of x minus x bar squared, plus the sum from I is equal to 1 to n of ei minus e bar xi minus x bar over the sum of the x minus x bar squared. Now, just as an aside, let's remind ourselves of the weak law of large numbers. And remember, the weak law of large numbers says that the probability limit of a sample mean is just equal to the expectation of that random variable. So the probability limit of the sample mean of x is just equal to the expectation of x. So because we're going to want to take the probability limit of beta 1 hat, a good step right now would be to divide top and bottom of each of our fractions by 1 over n, so that we can make our life easier later. So we're going to examine the consistency of this estimator. So in order to do so, we're going to need to take the probability limit of our estimator beta 1 hat. Now remember, with a probability limit, the probability limit of a sum is just equal to the sum of the probability limits. So we're going to take the probability limit of all of this, which is going to be equal to the probability limit of beta 1 plus the probability limit of beta 2 times by this thing plus the probability limit of this. The first term is easy to deal with because the probability limit of beta 1 is just equal to beta 1. Then we've got the probability limit of beta 2 times by this. Now, let's remind ourselves of some rules of probability limit. The probability limit of a constant times by a variable is just equal to a times by the probability limit of that variable. So if we're taking the probability limit of this is going to be equal to beta 2 times by the probability limit of all of that. So that's going to be equal to plus beta 2 times by the probability limit of 1 over n times by the sum of the z minus z bars, x minus x bar, over 1 over n times by the sum of the x minus x bar squared, plus the probability limit of 1 over n times by the sum of ei minus e bar xi minus x bar over the 1 over n times by the sum of x minus x bar squared. Now the second rule of p-lims that we're going to use is that the p-lim of a ratio is just equal to the ratio of the p-lims, provided the p-lim of the denominator, in this case p-lim of b, exists and is non-zero. So we can rewrite this as being equal to beta 1 plus beta 2 times by the p-lim of 1 over n times by the sum of z minus z bar, x minus x bar, over the p-lim of 1 over n times by the sum of x minus x bar squared, plus the p-lim of 1 over n times by the sum of ei minus e bar xi minus x bar over the p-lim of 1 over n times by the sum of x minus x bar squared. Now, in order to move further, we're going to need to use our weak law of large numbers. The weak law of large numbers says when we're taking the p-lim of a sample mean, we converge with probability towards the expected value. So we're going to use this in order to evaluate our p-lims. But what it means is that anywhere within our p-lim where we have a sample mean, that's going to convert into an expectation. So we've got some sample means explicitly labelled, but also whenever we're taking 1 over n times by the sum, we're explicitly taking a sample mean. So anywhere where we've got a sample mean, effectively we're going to replace it with an expectation. So we can rewrite this as being equal to beta 1 plus beta 2 times by the expectation of z minus e of z times by x minus e of x. So we've replaced the z bar with an e of z, we've replaced the x bar with an e of x, we've replaced the 1 over n times by the summation with an expectation, and this is all just due to the weak law of large numbers, divided through by the expectation of x minus e of x squared plus the expectation of doing exactly the same with this case, e minus the expectation of e times by x minus the expectation of x divided through by the expectation of x minus e of x squared. But hopefully you recognise the things on the numerator and the denominator. This is just our definition of a covariance between z and x. The denominator is just the definition of the variance of x. Here we've got the covariance between little e and x. Here we've got the variance of x. So our probability limit is going to be equal to beta 1 plus beta 2 times by the covariance between z and x over the variance of x plus the covariance between e and x over the variance of x. Now we need to go back and think about our assumptions. We assumed at the beginning that the expectation of EI given any set of x is going to be equal to 0. Now it follows from this that the covariance between e and x is going to also be equal to 0. So that means that the numerator of our final term is just going to be equal to 0. So this whole term vanishes. So provided the e term is unrelated to the x, then this final term vanishes. But we also are told that the covariance between z and x is non-zero. So that means that our probability limit of beta 1 hat is going to be equal to beta 1 plus beta 2 times by the covariance between z and x divided through by the variance of x. So this leads us to some conclusions. Now, when we're taking probability limits, we're essentially looking at what happens to our estimator in large samples. And we can think of this term here as being the bias to OLS from omitting the variable z in large samples. So if beta 2 is non-zero and the covariance between z and x is non-zero, then not including z causes bias. So remember, beta 2 is the marginal effect of z on the dependent variable y. The covariance term is just the covariance between z and x. Now, if beta 2 was 0, that would mean that z was not a determinant of y and would not appear in the error term. But even if it's correlated with x, if z is not a determinant of y and beta 2 is equal to 0, you're not going to get bias. Similarly, if z is a determinant of y and beta 2 is non-zero, if it's not correlated with x, you're not going to get any bias. So if beta 2 is non-zero and the covariance between z and x is non-zero, then omitting z will cause bias in large samples and causes the estimator to be inconsistent. If either of these are 0, then omitting z doesn't cause any problems.